Hello, everybody, and welcome back to the final afternoon of Build Stuff 2021, our state-of-the-art hybrid conference. We've got real speakers watching real audiences. We've got online speakers watching online audiences, or the other way around. And we've got vice versa in both cases. We got speakers on the big cinema screens out there in Vilnius. Hello to everyone who's watching us from the Kinoplex. And of course, we got folks tuning in from all over the world to watch the amazing speakers and sessions and content that we have for you today. It is my pleasure to welcome to our Jupiter virtual stage somebody who probably needs no introduction. He's literally written the book more than once on designing microservices, microservice architecture. He's here today to talk to us about hiding the lead, coupling cohesion and microservices. Please welcome Sam Newman.
Thank you so much, Dylan, for that lovely introduction. I wish I could be with all of you, but it turns out with a hybrid event, being with all of you would mean being in both Vilnius and many people's bedrooms and offices. So that would be a weird experience. But nonetheless, I'm really glad that we were able to make something work that allows us people to accommodate all of our ability or inability to travel and mingle. So this is a fantastic, and hopefully we'll be able to do many more things fully in person in the future. But if not, this is an amazing kind of way of bridging that gap. I have written books. I have arguably some people would argue, written the same book 3 times, but repetition is the soul of, I don't know, comedy, brevity, a steady income stream. I haven't yet worked that one out. I also, when I'm not writing books and doing presentations, I do actually work with companies building microservice things, but we can talk about that another time. I'm engaged by the idea of microservice architectures. I do not think that they are the perfect architecture. In fact, I think they should be the exception, not the norm. I think most people would be better off with a simple single process monolithic architecture. But nonetheless, if you're going to use microservices, you should be taking advantage of the key benefit that they give us, which is this idea of independent deployability. And so when you're thinking about the choices you make around your microservice architecture, the idea of independent deployability is the biggest thing you should be focusing on. And this is the ability for you to make a change to a single microservice, deploy a brand new version of that microservice into a production environment, release that functionality to the users of your software. And that's great. It's fantastic. This is all actually, when you get down to it, about reducing batch size. The kind of way we view microservices was heavily influenced by continuous delivery. And one of the main tenets of continuous delivery was to reduce batch size, which in turn allows you to release for more often because the releases themselves are smaller in scope. And so we're picking a microservice architecture partly because we want to reduce the scope of releases and allow us to be braver in how quickly we change our software. So this idea of independent deployability is really super important, not only in helping us do things like continuous delivery, but also really in somewhat justifying the complexity that microservice architectures bring. I still get amazed by the number of people that start building microservice architectures, fail to achieve independent deployability, and end up with a system that is significantly more complex and harder to maintain than what they had before. And at the same time, they're releasing less frequently. And that just sounds like a bad time all around. So for today, I wanted to drill into some of those things that you need to do well in order to make independent deployability work for you. When we get down to it, how we think about independent deployability and how we achieve it really comes down to kind of reasoning sensibly about the interactions between things. So in this example here, we see the accounts microservice has sort of a consumer, the customer service. So when we deploy a brand new version of our accounts microservice, we have to think about what impact we might have on the other microservices that sit in the ecosystem. The inherent paradox of a microservice architecture is that we kind of want to consider these things to be independently deployable units. But fundamentally, a microservice architecture only exists because of the collaboration between these things that we also want to see as being independent. When I make a change to this accounts microservice and deploy a new version, one of the utmost questions in your mind has got to be, am I sure that I'm not going to somehow break my consumer? Because guess what? If I break my consumer when I deploy my new microservice version, this is something that could well result in a production outage. And nobody likes production outages. The way we achieve this is by making sure that when we change microservice, that we make sure that the interfaces that our microservices expose have a degree of stability. So when I make a change to the interface that the accounts microservice provides to the customer service consumer, I want to make sure that I haven't changed that interface in such a way that I've basically broken compatibility. So I need to create stable interfaces on my microservices. Therefore, maintaining backwards compatibility is super important. A quick history lesson. Many, many years ago, most of our software ran on these things called mainframes. I am old enough that I have actually deployed software that run on a mainframe. And there's still a lot of these lurking about, especially in banks. It turns out they're very hard to kill. But it used to be that the whole world computing was mostly done on a very small number of very large and expensive machines that look a bit like this. Now, over the years, these mainframes became more and more powerful. And as a result, we were able to write more and more complex programs. People started realizing that managing these programs as they grew in scope became quite difficult. And we're talking here at some, the early stages about, writing programs that were on punch cards. At that point, an extent of your program organization was having a filing system for your cards. But as those things moved into being more textual representations, it's like, well, how do we group and organize code so our bigger programs are easier to work with? And this ultimately is where we came to with modular programming. The idea behind modular programming is that we can take a big problem space, a big program, and we can break that program down into modules. And these modules, when linked together, constitute our larger program, but each of those modules can be addressed and developed to some degree independently from one another. This gives us a way of decomposing a big problem space into many smaller problem spaces, which are much easier to reason about. David Parnas, back in 1971, wrote the now seminal paper on the criteria to be used in decomposing systems into modules. And I have said that an awful lot this year because I've been talking about Parnas's work a lot in the last few years, because I've increasingly realized since writing my first book on microservices back in 2015, that microservices and modules have an awful lot in common. When Parnas was looking at how we should design modular software and what makes for a good module, he kind of came up with 3 key criteria that for him said, these modules are working well, or this is a good way of using modules. And so he said that when done well, a module should help us, a modular architecture should help us improve development time. This because it allows work to be done in parallel. I can have different teams working on different modules. It should also make it easier for us to understand the system. It improves the comprehensibility of the system. We can understand how a module works in isolation, and we can therefore also start to understand how that module works in terms of its connectivity to the larger system. There's almost like this recursive property of comprehensibility. We can look at a module in isolation. We can also pull our thinking up and look at the modules as they are connected together. And the other thing that modules should give us is flexibility, the ability for us to change modules independently from one another. And this starts to sound a little bit eerily familiar, doesn't it? In many ways, this sounds like independent deployability. So we had flexibility. Can I change things independently from other things? And then we have microservices with independent deployability. Oh, it's spooky. It's almost like they're the same thing. So modules allow for independent working, fantastic. And also, of course, modules allow for reuse, and that's great. Now, with modular, say with monolithic software, typically all of these things are running on the same computer, although describing a mainframe as a computer is damning it with faint praise when you compare it to, say, your laptop. When we moved into the world of modular monolithic software, typically all of these modules would be running on a single computer as well. And so when we look at modular monolithic architectures, typically the challenge with them is that, even if we define our module boundaries well, we can get a degree of independent development, but that ultimately the act of deploying a modular monolithic system still involves a static linking activity. I'm collecting those modules together and I'm deploying them all at once. Now, mainframes, of course, were a thing. They are still a thing for some people. But when I started programming professionally, by which I mean I was actually getting paid for it in the mid-90s, we were sort of at that tipping point where we were moving from mainframes and mid-range machines, which I worked on very early in my career, moving more towards what we might now consider to be more modern server-based infrastructure. We went from having a small number of very large, expensive machines to having a large number of very, relatively speaking, inexpensive machines that nonetheless had quite a significant degree of computing power. And this sort of led to us thinking about our modular architectures more in terms of those modules now running on different computers. And so for me, this is what a microservice architecture fundamentally is. It is a modular architecture. The difference, though, is that these modules now run on different computers, and the communication between these modules is being done normally via some kind of network protocol. So inherently, microservices are a modular architecture. They are also inherently a distributed system. By running these things on different computers, aside from the fact this allows us to mix and match different technologies and opens up opportunities to scale our application because we're running on different processes, it also makes it much easier to achieve independent deployability because we have the process, and typically an operating system process, as a unit of deployment. I can redeploy a module if it's a microservice without having to shut my entire system down, hopefully. So I think when done right, microservices are a form of modular architecture. The good thing about that, it means is that we can use all the knowledge that we've gained about how to do modular architectures well and apply it in the context of microservices. And here, of course, I need to raise a cautionary note. As an industry, we suck at modules. And in fact, most of the modern programming languages we use have very poor concepts of modules and modularization. When you really get down to what we would like to have from a modular architecture, if you see the sort of capabilities that we get from, say, the JVM or the .NET CLR, they're actually really not that much better than what we had in the past. And certainly none of them come even close to what Erlang could do 15 to 20 years ago. So I do want to say that there's an extent to which maybe a little bit of our technology is lagging here, but nonetheless, as an industry, we don't seem to have understood the value that modules bring. When Parnas wrote that paper back in 1971, what he was trying to explore was how do we define those module boundaries in order to get the best out of them. So he looked at a problem, and he looked at solving that problem with different styles of modular architecture. So in one example, he took those modules and said that each step in this workflow was a discrete separate module. So you went through module A, then B, then C, then D, then E, kind of a linear use of modules. Some people refer to it as almost like a sausage factory type design. And the technique he actually came up with that was much better was to instead start to look at separating out the code that changes frequently from that code that doesn't change frequently. And the idea being that you find the code that is more stable and that you use that more stable code to form the APIs of your modules and to hide the more frequently changing functionality beneath those module boundaries. And this is a technique that he described as information hiding. That is, when you're designing a module, what you're aiming to do is to hide that functionality which is going to change frequently. So if we look at modules in the context of microservices, how does this example of information hiding play out? Well, let's start off by looking at an example where we aren't doing information hiding. So here is an accounts microservice. We have these blue dots, and they represent in-memory data structures or low-level methods. We have data in a database. And what we've done is we're all busy, we're all short of time. And so somebody else in our organization says, can I get hold of some of your stuff? And we go, look, I want to go to the pub. So yeah, sure. I'm just going to open up access and you can access it. So here, the shipping microservice, which is a consumer of our accounts microservice, we've given them the ability to reach deep into our internal implementations. They're directly accessing database tables, low-level methods, in-memory data structures. Because why? Because it's quick and it's easy and we are all time poor. And what could possibly go wrong? The issue, though, now is that this external consumer is a different service that's got a different runtime, that's probably owned by a separate team, is reaching in and using parts of our application that we are trying to own and manage and control. Now, when you come to work on this system, you don't want to break things. You don't want to break production. You don't want to break the consumers here. You don't want to cause problems in production. But how much confidence do you now have when you make a change to the accounts microservice that change can be made safely? What things can you change with confidence that you won't break somebody else? Can you change a database constraint? Could you change the name of a column? Could you add a new column? Could you make a column that was previously nullable now not nullable? Could you change a method name? And you were like, well, maybe, maybe not. And if I get it wrong, production outage time. With information hiding, what we're trying to do is to hide things. And from the sort of more generic concept of information hiding is hiding things that are most likely to change behind a stable boundary. The way I choose to interpret this is I am going to hide everything behind a stable interface unless it is explicitly needed. It is much easier to expose information and data after the fact than it is for you to hide data which you'd previously exposed and now find is causing you a problem. So actually, in general, you should be quite parsimonious, quite limited in what things you allow to be leaked outside of your service boundary, because exposing it later is always an easy thing to do, but hiding it after the fact is always going to be very difficult. So in this example, we've made a bit of a change. We've decided to be much more explicit about the service interface that we expose. We say, look, this is the world we share with the shipping consumer. We are going to create an explicit service interface. And that word explicit is important. When we make that service interface explicit, it is clear to the consumer in terms of what they can expect for us to provide. It is also clear to us as to what we need to continue to provide if we want to maintain a stable interface and be able to do things like independent deployability. So what you want to do for a developer working on this accounts microservice, it wants to be super clear as to what expectations they have to continue to provide and what parts of the code base can be changed freely without concern about breaking compatibility. So these things in your hidden world, that's yours. You can do whatever you like in that world. You can make whatever changes you want. And as long as you maintain compatibility of that external interface, you're good to go. It also follows that any code or functionality or configuration that defines that explicit interface can be code over which you have maybe a high degree of oversight. Maybe you always want to have a second pair of eyes on those changes that are being made. Maybe you want to have additional types of testing being used in those areas. And this would be an example where you might do things like consumer-driven contracts. I also, though, think these things start even easier than that. If you're going to expose a service interface, use an explicit schema. This will allow you to actually not only see what the structure of a service interface is, but you can also programmatically catch breaking structural changes in microservice contracts before you even check in. If you use JSON schema, if you use open API definition, if you use protocol buffers, and those three is already a large amount of the kind of communication protocol codexes that people are using, then you have the ability to run tools like Open API Diff, for example, that before you even check in will say, oh, you've changed the schema. You seem to have removed a field that was required previously. Are you sure you want to check in? Because this is going to be backwards compatible. This is kind of analogous to a statically typed language giving us type checking when we compile, right? If we have an explicit schema, we get a degree of checking of the structure of our interfaces before we even push to production. Now, you also still need to do testing, but if you have explicit schemas and schema compatibility checking, then the testing you do can be much more focused on the behavioral semantics of your interface. So let's move on from information hiding and talk about other things that have occurred in the area of modular programming and structured programming. And again, here we need to go dumpster diving through computing's past and read books like Structured Design or The Practical Guide to Structured Systems Design by Paige Jones. Now, I started doing all this research during early stages of lockdown, which meant I was denied access to the Canterbury University Library up the road. And getting hold of these books is remarkably difficult because some of them are ridiculously expensive. Luckily, I've got Kevin Henney's email address, so I just pinged him and asked him to read out stuff from his own personal library, which helped me out immensely because there's a load of great ideas and research in these books talking about how we think about the structure of programs. And so structured programming is where we get terms like coupling and cohesion from. Now, it's worth saying the concepts of coupling and cohesion, certainly at this time, a lot of that work is focused on these things at the code level, and not all of these ideas apply maybe at a larger scoped service level, but there are still lots of ideas that we can take from this world. We hear coupling and cohesion so much, and we typically talk about coupling and cohesion in terms of the extent to which we want one. We want one or the other. And really what we're normally looking for is we want a low degree of coupling, we want low or loose coupling, but we want strong or high cohesion. And typically we say, that's what I want, that's good. But what does this actually kind of mean? Now, the problem is a lot of the definitions of these terms are often defined in terms that are around maybe kind of quite low level code concepts. And so we often have to look for different takes on these themes. One of the nicer definitions I've heard of cohesion is this idea that the code that changes together stays together. And the idea being there that, if I want to change a piece of code, I don't want to have to go and change it in 10, 15, 20 different places, because not only does that take me longer, but it's also error prone. The other issue, of course, is that when sort of the same sort of code, or the code that should change together, is spread across the system, there's a possibility that that code may not agree with one another, and you might get some weird inconsistencies in behavior. Systems that have weak cohesion include kind of layered architectures, where just to roll out a very simple change in functionality, you end up having to cut across multiple layers of your architecture. These things in turn can lead to the distributed monolith, where you have a distributed system, but because you always have to change things cutting across all these layers, you're constantly deploying the entire system together. And distributed monoliths tend to have all of the problems and downsides of normal monolithic architecture, in addition to having all of the downsides of a distributed system like microservices do, but not having enough of the upsides of either to be worthwhile. The distributed monolith in many ways is the worst case scenario. And certainly when I encounter this with some of my clients, often my advice is, let's merge everything back together into a single monolith and start again. There are other types of areas where poor cohesion can manifest itself in a microservice architecture. Let's take a look at a very simple example of a piece of data. So here is an order row that's in a database somewhere, and I'm stripped out lots of data. So you have an ID here, and we have a status of that order. And we have an order microservice, and we have a warehouse microservice. And for some reason, we haven't read any of my books, and we've thought it's a good idea to have multiple microservices reading and writing from the same database, which you shouldn't do. But let's imagine we have, because you haven't read my books. Hopefully you've bought them. I do have a mortgage to pay for. And we've got the order microservice here. And the order microservice handles changing the status of an order and moving it into the statuses of placed, paid, and completed. The warehouse microservice is responsible for different types of state transitions around an order. It can set that order into status picking and shipped. So both services contain some functionality related to how this one thing, an order, can change. Do they agree with each other? Do they both have the same view about what the allowable state transitions are? Because if they don't agree, you can get into some weird issues around data consistencies. And even if they do agree on how an order should be changed and managed, that implies that basically logic around that is now spread across my system. So now I've got probably code and at the very least behavior duplication. So when you have weak cohesion of systems, you end up with either distributed functionality, which costs you more time to upgrade, or differing functionality, which doesn't agree with one another, leading to all kinds of data issues. Instead, if we're looking at this as a microservice architecture, whenever we see code like this, and again, with our domain-driven design hat on, we might look at this and say, well, the order is an aggregate. We think about management of that aggregate like we would think about management of a state machine, and we would want the ownership of that aggregate to reside in one single piece of code, one single entity, in our case, a microservice. So you'd be much better off to say the thing that knows how to change orders and knows what the allowable set of state transitions is should be a single microservice that improves the cohesion of our system and in turn reduces the coupling. So let's talk about coupling, the different ways that coupling can manifest itself in a microservice architecture. Because there's this weird challenge with microservices, and I talked about it at the beginning. There's this inherent paradox, which on the one hand, we want microservices to be things which are independent. And the best way to make sure that something's independent is to make sure that it never talks to anything. But microservice architectures are inherently about the interactions between things. A microservice that doesn't talk to anything and where nothing talks to it isn't really a microservice, I'd argue. It's a standalone application. And if you can build your software like that, then well done you. You should absolutely do it. So microservices want to be independent, but we accept that some degree of communication is required. So let's talk about coupling and the different types of coupling that you might encounter. Coupling in general, we can see as the degree to which changing one module requires a change in another. In our case, the degree to which changing one microservice requires a change in another. This speaks to the idea that coupling has strength. So, there is some changes which can be made safely and some that aren't. The more coupled you are, the more likely changing one thing is going to require changing other things. Now, I've tried to kind of come up with a very simple categorization scheme for different types of coupling. Some of this is based on prior art in this space, and some of this is kind of stuff I've tried to amalgamate. Again, reflecting the fact that a lot of the original terms in this space were more about code-oriented concepts rather than, say, service architectures. But the kind of three key types of coupling that I'm going to describe today are what's called domain coupling, common coupling, and content, otherwise known as pathological coupling. That doesn't sound good, and you'd be right, it isn't good. These are on a spectrum going from left to right. As we go from the left, we have the looser forms of coupling, and as we go to the right, we have the stronger forms of coupling. And so when we find these types of coupling in a microservice architecture, what we're often trying to do is replace that form of coupling with a looser form of coupling, trying to kind of shift us back towards the left. So let's take a look at domain coupling, which to an extent is a kind of coupling which is somewhat unavoidable in a microservice architecture. So here we've got something we've called an order processor. We won't get into the name of an order processor right now, but let's just talk about what that order processor does. Its job is to manage the process of taking payment of an order and shipping it. So it's like an e-commerce company you can think of here. So that order processor, one of the jobs it needs to do is it needs to reserve stock in the warehouse so that we know an item is available, so it can later on be packaged up and shipped off to the customer. We reserve the stock with the warehouse, and then we take payment from the customer. And these things, they could be done in parallel or sequence. We don't really know at this point. So the order processor knows that stock needs to be reserved, but it's not responsible for how stock is reserved, but the warehouse is. The warehouse owns that responsibility. So we have to communicate with the warehouse and ask for stock to be reserved in this model. So this is a form of domain coupling. Effectively, the order processor is coupled to the domain protocol that the warehouse microservice provides. In REST circles is what's called the domain application protocol. Now, if we change fundamentally how stock reservations are done, that could result in a change to the order processor. But that would typically normally mean that you've changed the business processes quite significantly. So there's some degree of interaction here which are kind of unavoidable. Likewise, if the payment microservice changed how payments are done, and now we've got a very different way of how payments are being handled, the order processor might also have to change. The warehouse and payment microservices don't communicate with one another. A change in payment isn't going to affect the change in warehouse. So with domain coupling, there's always an extent to which you've got different domain concepts communicating with one another, and that's kind of unavoidable. What we can still try and do is to reduce how much of it we need, and also look for potential signs that we might have too much domain coupling in one location. Something called an order processor is always the kind of thing that gets my spider senses going. Processor implies like a whole load of generic stuff going on. And the next thing you start saying is, how many microservices does the order processor talk to? If it's one or two, it's probably okay. It's talking to 25 different microservices. It is now much more vulnerable to any changes in the domain protocol in your system, and it's often a sign it's doing a bit too much. So, I always look for those things. But to some extent, domain coupling is sort of unavoidable. You'll try and limit it, but you're going to have some degree of it. Otherwise, you don't really have an interconnected system at all. Let's look at some slightly worse form of coupling. And this is maybe we talk about common coupling. And typically this refers to common data sources. So this could be like a shared cache. This could be actually, say, a shared database. So the database is kind of defined and managed by an external party. But in this example, each of these microservices makes access or does stuff with this sort of bundle of data. So here the warehouse microservice is directly updating stock levels. The order processor is reading those stock levels, and the forecasting engine is also reading those stock levels. Now, if I change that structure of that stock level store, it's going to break all of those microservices. So I effectively have to treat that stock levels thing like a data structure. The reason, like a contract, a data structure with a schema, basically. The reason this becomes problematic is that often these types of shared data stores aren't something as simple as this is the item in stock and this is how many copies we've got. They actually become like giant databases. The more complex these data structures become, the more complex these shared data structures become, the higher the degree of coupling you're going to have and the much more vulnerable you are to changes. So if you do have situations where you do need to have some form of shared data like this, you want to keep it incredibly simple in structure and also recognize that any changes in that common data structure could have significant ripple effects. I would still strongly consider having an explicit schema to make sure that it's easy for you to know if these changes can be made in a safe fashion. If you were, say, storing, I don't know, binary blobs using protocol buffers, that's easy to do. Or a relational database actually has some benefits here because it has an explicit enforced schema inside it. The worst form of coupling we've got is what's called content coupling. This is where you've got a microservice which has its own state and behavior, but we've somehow allowed external parties to reach into the internals of our system. So here we've got our order processor, and our order processor is being well behaved. It is going to the actual service interface that our order microservice exposes. It's using the REST API or whatever else it might be, and it's delegating an awful lot of work to the order processor. If it wants to change the state of an order, it is asking the order microservice, can you please make this change for me? The order processor gets to manage that state machine and say, yes, I can, or no, I can't, because what you're asking for is just wrong, right? You know, if you're kind of implementing a state machine and someone tries to initiate an invalid state transition, the state machine should error. And when we implement kind of our management of our state like this, it's much easier to kind of eliminate invalid state transitions. But oh no, we've let the dastardly warehouse sneak around behind our defenses and directly manipulate our data. We've now completely bypassed all information hiding. There is no information hiding at this point. As someone working on the order processor, on the order microservice, it's totally unclear to me as to what changes can be made safely. This is the worst form of coupling. It results in a complete paralysis. It results in a huge productivity hit. And there's a reason why it's also known as pathological coupling. What would be a way to fix this? Well, stop warehouse directly manipulating data, have it use the same service interface that the order microservice exposes, have the order microservice only expose the bare minimum that is needed, and allow it to own how these entities can be changed and managed. And that would result in a much simpler, easier to manage system without the degree of coupling. It's effectively where this is where we're replacing sort of content coupling with more domain coupling. So the types of coupling we get in microservice systems are many and varied, and there are other types I go through in my book. But in general, what we're trying to do here is to kind of use the looser forms of coupling. Something else I didn't have time to go into is the interaction and the interplay between sort of coupling and cohesion. What you'll find is that as you increase cohesion, you decrease coupling, and vice versa. These two ideas are inextricably linked. So often you can make you can improve your story around coupling, you can reduce coupling just by improving cohesion. But likewise, when you see a system that has poor cohesion of business functionality, especially, you're likely going to see a high degree of coupling. If you want to know more about that, read chapter 2 of my book. It goes into a lot more detail. In summary, information hiding is vital for microservices if what you're trying to achieve is independent deployability. Right? This is really key. And if you remember nothing else from this talk, please buy my book. We've been in a pandemic. I've got to sell copies and I've got a mortgage. We are doing translations. They're not out yet. But the second thing you should remember is with microservices is this idea of information hiding. When you're creating a microservice boundary, think outside in. What do my consumers need, and only expose the bare minimum that my consumers need. This will ensure that you're keeping as much functionality and behavior hidden from the outside world as possible, and that will make it much easier for you to achieve independent deployability. When you start looking at coupling, some coupling is worse than others. Some interactions between microservices is to an extent inescapable, but try and keep it at that level of domain coupling at best. And if you can bring all these ideas together, information hiding, low coupling, strong cohesion, that's going to help you achieve independent deployability. Now, in all seriousness, if you did want to take a look at my book, you can go read it for free. You can go and sign up at O'Reilly for a free trial. It's like a 7-day free trial. And then you could read chapter 2 probably in an hour or so. So you could go read that one chapter now for free, and there's no obligation to pay. Although, do think of the children. And if you want any more information about the work that I do, you can find that over on the internet at my website, or hit me up on Twitter. Now, I'm hoping I've stuck the landing well enough there, Dylan, that we've got time for some questions.
We do indeed have time for some questions. First of all, thank you very much for that. That was excellent as always. Now, let's just take a look And we have folks, those watching us on Pine, we currently have no questions in there. They're all too busy buying your book. You've distracted them.
That's what it's going to be.
Buying for copies. So we do actually have someone saying, I'm in O'Reilly already, so it's already on my reading list.
Oh, okay. They're good.
But no, we, as I say, to a time like this, you've achieved complete enlightenment.
Yes. Or they're all asleep. I mean, either way, that's arguably a form of success. I've given them a nice relaxing nap.
You got 111 people, and you started out with 90, so you've had people consistently joining over the course of the of the stream. So yeah, the numbers are looking pretty. We know people are out there, but you know what it's like. You're on that screen, and in the middle of that screen, they probably got their boss on Slack complaining.
Yeah.
So,
well, if people do remember a question they wanted to ask me later on, probably the easiest way to get hold of me in general is just on Twitter. So you send me a tweet on @SamNewman. I'm very happy to answer any and all questions over there. And so if they do kind of wake up in a hot sweat in the middle of the night, wishing they'd taken this opportunity, go ping me on Twitter, and I'll happily respond over there.
Fantastic. So we are actually, Sam, going to invite you to join our live Zoom Q&A session for a few minutes now. So folks, if any of you do have any questions that you don't want to wait until the middle of the night and then ask Sam on Twitter, please jump over. Sam, I'll drop you the Zoom link for that here in a moment. So the link for those folks watching on Pine is there. Sam, the link is, where's my chat window gone? There it is. So the chat window link is there. If you want to hit that, you can go over, hopefully meet some folks, answer a couple of questions. If there's no one there, then your work here is done. Thank you so much for joining us. Thank you, folks, for tuning in. Those watching us live on the big screen in Vilnius, and those of you all over the world watching us on the small screens or big screens, however big your screen might be. We're taking a short break. Grab a cup of coffee, folks. Stretch your legs. We'll see you back here in a few. Take it easy.
Thanks, everybody.